Hello, welcome to the live streaming seminar on AFM probe cantilever selection. This is the fourth of 5 webinars we're doing this summer on sort of the basics of atomic force microscopy. My name is Paul West, and I'm the president of the AFM workshop, and I've been working in this area for many years. And so I'm hoping that the information we give you today can help you with your AFM projects. So the agenda for today's presentation, I'm going to go through an introduction, a little bit about probes for atomic force microscopes. Then we'll talk about the cantilevers. Then we'll talk about the probes. And then I'll give an idea of how you would go through a selection process for the correct cantilever probe combination for your experiments or your measurements. First, let's talk about terms, because some people call this entire thing the probe. It's actually broken down into 3 sections: the chip or the substrate. The second is the cantilever, right here, that's what comes out. And then the tip or probe. And so when we talk about these things, we talk about the cantilever, the tip or probe, and the chip. There's 3 separate things. And many people call this all the probe, or some people call it all the cantilever. But it's made up of 3 separate sections. These cantilevers and probes are manufactured using anisotropic etching of silicon. And this is a technique which developed for MEMS back in the 1960s and 70s. And one of the things about doing this type of fabrication is it gives a very large variation in specifications. I'm going to talk about that a little bit. These are some pictures I grabbed off the internet from Stanford's website, and they show some of the capabilities of doing anisotropic etching in silicon. And what happens is the etching occurs preferentially and gives these structures in the silicon. There are many vendors for these types of probes. I've listed them here. They're Applied Nanostructures, NanoWorld, Olympus, Bruker, Naga Needles. There are others. And what you need to remember is when you go to buy these things, most of these vendors or these manufacturers have distributors that sell these things. And so you'll find that applied nanostructure probes are sold through many different distributors and different types of companies. And same with NanoWorld probes and Olympus. So you'll find these probes available through many different sources. One of the questions that comes up when people start to do atomic force microscope is this first question: what's the lifetime of a probe? How long does it last? And so the answer to this question is it depends. And these are the things that it depends on right here. It depends on tip approach. So when you're running your microscope, if you're able to do a proper tip approach and the probe comes down and very gently comes to the surface, the tip will be preserved. However, if you're not careful in doing the tip approach and maybe the instrument's not tuned up, it'll hit. And if it hits, it could break the probe. Second, it depends on the scan parameters you're using. If you start to scan too fast and the feedback loop in the microscope can't keep up, the probe tip will tend to be chipped off. And then what will happen is as time goes on, you'll see the resolution of your microscope degrade. Also, it depends on the vibration environment of the microscope. So if the microscope is vibrating a lot and the tip is being pushed into the surface of the sample, then that'll cause the probe to break. So if you can master these 3 things, that is getting a good tip approach, and you're able to have the right scan parameters, and you're in the right vibration environment, a probe can last a week, even a month. And so you'll see some people that are very experienced with running AFMs will use a probe for a while and they'll take it out of the microscope and put it back in a box. And then when they want to use that probe again, they'll take it back out and use it. So again, this really depends on several factors. So the first thing that you need to be familiar with is our cantilevers, and that's one of the parts of the product that you purchase. And the cantilever is important because it establishes the probe to surface force, or actually the pressure of the probe onto the surface. And when you look at cantilevers, they kind of fall into 2 general categories. They're vibrating and non-vibrating. So people call vibrating tapping, intermittent contact, non-contact, near contact, There's a number of different trade names that are used for vibrating, AC modes, and then non-vibrating. And non-vibrating is when the probe is not vibrating or the cantilever is not vibrating, and that's often called contact mode. So you need to be aware of cantilever mechanics, and that is the equations or the parameters that characterize a cantilever. There's two basic parameters that characterize a cantilever: the force constant K, which is shown here, the formula for it, and the resonant frequency F. Okay, K is a measure of the stiffness, and it's derived from Hooke's law, and that's kind of how hard it is to push the cantilever up and down. And so the parameters that establish the force constant have to do with the Young's modulus, the width of the cantilever, and the thickness over the length to the cube power. So it's very dependent on the thickness and the length of the cantilever. So if the length gets longer, the force constant goes down very rapidly. The resonant frequency, again, depends on these parameters, and so these things can be calculated based on the materials that you have. Now, one of the problems is that when you buy these cantilevers, they have a large variation of force constant specifications and potential resonant frequencies. I have here the specifications from a typical commercial general purpose probe. And the length can vary from 215 to 235 nanometers for this probe, the width from 38 to 48, and the thickness from 6 to 8. So there's quite a large variation. And if you plug those in and you look at the extremes of what these force constants and resonant frequencies can be, it's quite large. So the force constant can vary by a factor of almost a little over 3, from between 25 newtons per meter and 95 newtons per meter. And that can also be nanonewtons per nanometer, or that's the same measurement, the same units. But that's quite a large variation. So what people like to do is you can use what's called the method of Sater. You can look that up on the internet, and you can go out and get a spectrum analyzer. You can buy these on the internet for not very much money, and you can measure the resonance frequency and get the thermal spectrum of the probe. And then there's different calculators out there, and what you do is you put in the length of the cantilever and the width of the cantilever, which you can measure with your video microscope that's in your AFM. Just make sure it's calibrated, and the resonant frequency, which you can measure with your spectrum analyzer, and the quality factor, which you measure with the spectrum analyzer, and you can calculate the force constant. And so this force constant for this particular cantilever came out to 46.5 newtons per meter. So this is something that you can do quite easily. So the question is, what kind of cantilever? Why would I use either a vibrating probe or a non-vibrating probe? So it really has to do with the amount of force that's imparted between the probe and the surface. And so for contact mode, the equation to understand force is given here. It's Hooke's law, and that is that the amount of force is proportional to the distance or the bending of the cantilever. So for a commercial cantilever, you can find force constants as low as 0.01 nanonewtons per nanometer. And typically, though, they're more like 0.1. But if you could detect a 1 nanometer change in the deflection of the cantilever with your light lever, then you can calculate very quickly that you can get a 0.01 nanonewton force measurement. And again, if you can detect a 0.1 nanometer motion of the cantilever, then you could get a 0.001 nanonewton. So that's kind of the limit. It's thousandth of a nanonewton with using contact mode. So vibrating mode is more sensitive. And in vibrating mode, what happens, of course, is that you have a free oscillation of the probe. And as the oscillating probe or vibrating probe approaches the surface, the vibrations or oscillations are dampened by the interactions between the probe and the surface. And then when that happens, you have two things that occur. One is you have a change in the frequency, and you also have a decrease in the amplitude at that particular frequency. And so about 20 or 30 years ago, Kumar Rakwimansingh and his researchers, Williams and Martin, his colleagues, calculated the theoretical limit based on a model of this particular frequency curve and the shift in the mechanics of about 0.0003 nanonewtons. Now, I'm not sure if anybody's ever actually proven this, and I suspect that there's other calculations of what the minimum force is you can do with vibrating mode. But this is maybe an order of magnitude or two more sensitive than the non-vibrating mode or contact mode. So, also with probes, with cantilevers, you can have coatings on them. And you can put a reflective coating to increase the light into the photodetector. And what the factor that determines whether or not you need a coating is typically your manufacturer and how the power of their laser and the sensitivity of their photodetector. So usually, if you use a microscope that uses coated probes, you always use one that uses coated probes. And if you don't, then you don't. So the materials for coating probes depend on the type of probe. The type of cantilever the material is made out of. And so if it's made out of silicon, quite often you use aluminum. If it's made out of silicon nitride, you would use gold. So again, this typically depends on whether the type of the manufacturer of your microscope. So for cantilevers, here's kind of a general rule. The tip sample forces are less for vibrating mode than non-vibrating mode. So what that means is for vibrating mode, you can use that on soft samples and hard samples. Non-vibrating probe or contact mode is typically used on hard samples. So in AFM Workshop, we almost always do our scanning in vibrating mode because that works for both soft and hard samples. Probes are very important for the microscope. This is an image taken from the Applied Nanostructures website. They're one of the vendors. And the probes are very important because they establish the size of what you're going to measure. And again, if you don't have really high resolution requirements, then you don't need such a sharp probe. Now, one of the things that's always important to remember is with atomic force microscopes, when we say we consider 10 to 20 nanometers low resolution. And for many other types of microscopes, like an SEM or TEM, that might be considered high resolution. So for 10 or 20 nanometer resolution images, not so important. But when you get down to the nanometer resolution measurements, it's quite important. So, so the probe in general should be smaller than what you want to see in an image. So I have here on the next slide the example of a probe going over a nanoparticle. And there's two things that you'll note here. The first is that no matter how sharp the probe is, you'll get the correct measurement for the height of the nanoparticle. And this is general for a lot of atomic force microscope measurements. That when you're measuring heights, that's the vertical dimension, the probe geometry is not so important. However, if you're measuring the width of it, it's quite important. And if the probe is much smaller than what you're trying to measure, then you can get a pretty accurate measurement. But if the probe is on the same order of magnitude as what you're trying to measure, as in this case, you'll get an artifact which is a combination of the probe and the sample geometry. So again, selecting the probe really is important to understand what the size of what you want to look at is. So this is an example right here of a general purpose AFM probe with a specification of a radius of less than 15 nanometers or a diameter of less than 30 nanometers. And these are 1 nanometer and 3 nanometer nanoparticles. And you see on the scale right here that this is 0 to 100 nanometers. So these probes, these nanoparticles, the shape of them are being broadened by the geometry of the probe. However, if you look at the height of these, it is correct. So this is some pictures taken off the NanoWorld AG website. And these are specialty probes. And there's a number of these things that you can buy. Super sharp probes, these are created by maybe etching of silicon. These are high aspect, they're created by maybe ion milling. This is a diamond coated probe. It has a 100 nanometer thick coating on it. And there's a number of these things. If you go to the manufacturers, there are people that put spheres on the end of probes. So there's a number of different specialty probes for different kinds of measurements. And so it's good to get these catalogs out, take a look and see what's available, and maybe you might find something that's useful in your measurements. Now, I would like to point out that when you get into these specialty probes, the prices do go up fairly dramatically. Many people like to do modes with their atomic force microscopes. For example, field modes, which include MFM and EFM. And in these types of measurements, there's a coating that's put on the bottom of the cantilever, and the coating could be some magnetic coating or some conductive coating. But what's important to remember is when you put that coating on there, it's put on with vapor deposition, what happens is the diameter of the probe increases. So if you start out with a probe that has a diameter of, say, 30 nanometers, and you put a 50 nanometer coating on it, the diameter of the probe gets much larger. So therefore, a lot of these field modes, the ultimate resolutions are not as good as they would be with a standard topography measure with an AFM. There's thermal modes, and you can put a thermocouple or a thermistor on the probe tip. And in doing this, you can make thermal measurements. And again, it's tough to make a thermistor or a thermocouple on the end of a probe that's going to be as small as a probe that's used for topography. Finally, electrical test modes. This could be conductive AFM or measuring parametric measurements. You put a coating on the bottom, just like this here, shown with the red. And again, most of these electrical test modes quite often are done with non-vibrating or contact mode. And so it can be quite good to use a diamond coating for these measurements because the diamond coating is much stiffer and the coating won't be rubbed off while you're scanning. But again, always remember the tip diameter tends to increase when you put these coatings on. So, the question is, which probe do I use? And so there's no direct answer for that. It really depends on your application. That's the most important thing. You say, well, what's my application? What do I want to measure? Once you understand what you want to measure, then you have to go through sort of the desired resolution. What probe do you need to achieve that resolution? Then you can look around at the different vendors and find the probes. Is my sample hard or soft? And then you start looking at the cantilever options you have, and vibrating mode or non-vibrating mode, and how much force is going to be imparted between the tip and the surface while you're scanning. Finally, if you're doing a mode, then you'll need to decide what kind of coating you're going to have on the probe and the cantilever. And so take a look at the different options available and the thicknesses. Finally, I'd like to mention that it does make a big difference if you're going to use do metrology measurements or visualization. If you're doing measurements with the probes, you're going to need, if you want really accurate measurements, accurate and precise measurements, as in a metrological measurement, you're going to need probes with much higher specifications, which are much manufactured to a much tighter tolerance. Visualization, quite often, if you're looking for a picture of the surface, the specifications of the probe are not so important. So I'd like to stop here and ask if there's any questions from the talk I've given so far. Okay, how to calculate acquire the Q factor. So to do that, what you can do is you can go on the internet and you can find a spectrum analyzer, or you might have a spectrum analyzer in your lab. If you write to us, we might be able to send you some suggestions. And you hitch that up and you measure the top minus bottom signal of the cantilever when the probe is away from the surface. So you're looking at thermal vibrations of the cantilever, and you store that with your spectrum analyzer. And then you measure Q, which is, I believe, the full width at half max at the designated frequency. So this is something you might be able to find on the internet, but we can help you with that. Okay, next question. How do we know the Young's modulus to calculate the spring constant? The Young's modulus for the material, you can look that up in a guide, in a physics guide. It's a materials property. It's an intrinsic materials property. Okay, are there any other questions? Okay, so I'd like to conclude by saying that when you select the probe for your microscope or the cantilever, what you have to do is look at the cantilever, look at the probe, and look at the coatings, and then make an informed decision. And again, the probe that you're going to use is going to always depend on the application. So that's the key thing, is decide once you know your application, then you can go through and figure out which probe you need. So thank you very much for coming on and viewing our webinar today, and we'd like to hear from you if you have any additional questions. Thank you.